The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Welcome back, everybody, to AO3. Today, we are going to continue the discussion of symmetry metrics, which we started last time. And this is actually what we have been doing. Okay, so the thing which we have been doing is to solve the normal mode frequencies of coupled system by looking at equation of motion nx double dot equal to minus kx. And in the end of the day, what we are doing is really to solve an eigenvalue problem, n-1k matrix eigenvalue problem. And we have been exercising this several times, last few lectures. And the n-1k matrix is actually describing how each component in the system interact with each other. Okay, so that's actually what we are trying to do in order to solve the normal modes. So we have been making progress, and we are increasing the number of coupled oscillators as a function of time. And now we finally arrived at our limit, which is infinite system, right? So basically, what we have been discussing is a special kind of infinite system, which actually satisfies translation symmetry, right? So in general, we don't know how to solve infinite system. If this system is really complicated, no symmetry, then who knows how to solve this, right? But very luckily, in L3, we got started to look at highly symmetric infinite system. And in this case, it's translation symmetry. And that is really pretty nice. And we can actually use this example to learn interesting effects, which we can see from the physical system we discussed here. So one thing which we have been discussing is the space translation symmetry matrix. As a reminder, S matrix actually is defined here. Basically, if you have a vector A which describes the amplitude of individual component in a system, basically this vector have AJ, AJ plus 1, AJ plus 2, blah, blah, blah. All those amplitudes are included in this vector. And what does this S matrix do is actually the following. So if A prime is equal to S times A, then the J's component of A prime will be equal to AJ plus 1. Okay, so that's actually what this S matrix does to A vector. Okay, so you can think about S matrix as an operator. It's actually picking up the AJ plus 1 component and move it to AJ in the new vector. Okay, so that's actually what this S matrix does. And we were talking about the eigenvector of S matrix. For example, if A is an eigenvector of S matrix, then we have this relation SA equal to beta A. So beta is actually the eigenvalue of S matrix. Okay, and we also discussed last time, that means based on this logical extension, AJ prime will be equal to AJ plus 1 based on the definition of S matrix. And that is going to be equal to beta times AJ, right? Because we assume that we assume that A vector is an eigenvector of S matrix. Okay, that means AJ will be equal to beta to the J A0, right? According to this relation. Therefore, we can conclude that AJ will be proportional to beta to the J. Okay, beta is still some coefficient which we have not determined, and it can be anything. Okay, so in order to consider a system of little mass which are oscillating up and down instead of going in one direction forever, or the amplitude grows, exponentially. And we also don't want the system to have amplitude goes to infinity when we go to very large J value or very small J value. Therefore, we limit our discussion in the case of beta equal to exponential IKA. Okay? In this case, the beta is the absolute value of beta is 1, right? Okay? And that means, okay, AJ is actually is proportional beta to the J, right? So if you take a ratio of AJ plus 1 and the AJ, the ratio is beta. If beta is not equal to 1 or its absolute value is not equal to 1, then this AJ value is going to be increasing according to a power law, right? So the amplitude is going to be going to very, very large value, right? And that corresponds to some kind of physical system, but not corresponding to oscillation, okay? And if we do this and assume that beta is equal to exponential IKA, okay, if we do this, what is going to happen is the following. So again, the ratio of AJ plus 1 and AJ is a fixed value, beta equal to exponential IKA. But what it does is not, instead of changing the amplitude, it's actually doing a rotation in the complex plane. Okay, so if this is a J plus 1, J plus 2, etc. as a function of J, the label, then what it does is that this operation multiplied by beta is really a rotation in the complex plane. And what we actually see in the physical system is actually a projection of this complex imaginary plane to the real axis. And that will give you a sine function and cosine function. So very interestingly, if we choose wisely the beta to have absolute value of 1, then that will give you a system which is actually oscillating up and down, and the amplitude is actually confined within some value. Okay, so that is actually quite interesting. The other thing which I would like to talk about is, okay, I choose to have exponential IKA as my beta. Okay, YKA, right? It looks really strange. Suddenly, K and A come into play, right? So what is actually the small a? The small a is actually the distance between little mass, just a reminder. So this is actually the length scale between all those little mass, right? Therefore, what I'm doing is to factorize out the length scale, and then we suddenly found that, okay, after I do this, I define beta equal to exponential IKA instead of exponential I theta, right? So you can also do exponential I theta, right? But instead, I give theta a fancy name, which is K times A. A is actually the distance between mass. Then something interesting happened because K suddenly also will have a meaning. It's actually the wave number of the resulting, it's actually the wave number of the resulting sine wave. Okay, so that's actually why we actually factor out this A factor. Then after that, we actually found that the amplitude will be proportional to exponential IJKA, and J is actually just a label of J's component in the system. Okay. So once we have solved the eigenvalue problem for the symmetry matrix S, as we discussed before, if you look at the slides, okay, if S and the n-1 K matrix, they commute, okay? Commute means that you can actually change S and n-1 matrix. You can swap them, okay, when you multiply them together, okay? If you can swap S and n-1 K matrix, that means they commute, and our conclusion from last time is that they will share the same eigenvectors, okay? Of course, not necessarily the same eigenvalue, but they share the same eigenvector. So that's a great news, because instead of solving n-1k matrix, which can be really complicated, depends on what kind of physical system you are talking about, I can solve S-matrix eigenvalue problem, okay? And then this eigenvector, which I just found here, is going to be the eigenvector of n-1k matrix. And that's actually really making things much easier, because now instead of solving eigenvalue problem of n-1k matrix, what I'm doing is just multiply n-1k times A, then you can actually obtain the normal mole frequency omega. Okay? So that's actually the great excitement. What does that mean? That means if you have all kinds of systems which are translation symmetric, you can have a line, you have whatever many people together, whatever a system which is shown here, they are all going to have the same eigenvector. You see, you already know how they are going to interact with each other, and what is actually the amplitude as a function of J, which is the location label. Okay? So that's actually really wonderful. So, in order to help you with understanding of this system some more, we are going to discuss another system, which is actually also very interesting. It's actually a spring. Okay, last time we discussed a spring and mass system, right? And we solve it together. And this time we are going to solve a system which is made of mass and strings. Okay, so let me actually so let me actually introduce you this new system we are going to talk about today. It has many little mass here from the left-hand side of the universe and right-hand side of the universe. Take forever to actually construct this system. Okay. Then my student actually carefully link them by strings, and that we make sure that the string tension, okay, is actually a fixed value, which is T. Okay, T is actually the string tension, and of course, as what we discussed before, the space or the distance between little mass is actually A. Okay, okay, so that's again the same length scale which we were using. And finally, in order to describe all those little masses in this system, I label them as J, J plus 1, J plus 2, etc., etc. Okay? So what the question we are asking is, what will be the resulting motion of this system, right? So what we can do is, as what we have done last time, right? We take J's object in the system, and we look at the force diagram, and that's to construct the n-1, to write down the equation of motion and also the n-1k matrix. So what is actually the force diagram? Of J's component. Okay, if I take this, so first I take my J's mass, and it's connected to two strings, right? So there are two strings connected to J's mass, okay? And of course, left-hand side you have another mass, right-hand side you have another object, okay? And I know the tension of the string. It's actually a fixed value, and the string tension is fixed at the T, okay? So in order to describe this system, I need to define my coordinate system, right, as usual. So what is actually the coordinate system I'm going to use? So I need to define horizontal direction to be x, and the vertical direction to be y. Therefore, I can now express this little mass to be the position of this J's little mass as xj and the Yj. Okay? I can do the same thing for the xj, for the left-hand side mass. It's xj minus 1, yj minus 1, and xj plus 1, yj plus 1. So to simplify the discussion, what I'm going to assume is that all those little mass can only move up and down, okay, instead of back and forth. Okay, so only one direction is allowed. And also, I assume that the up and down motion of all those little mass is really, really very small. So I can use small angle approximation. Okay, so therefore I can. This is actually the zero of y-axis when I before I actually move one of the mass away from the equilibrium position. So when the stream mass system is at rest, okay, not really moving, then all the mass are at y equal to 0. Okay? So now I actually move this mass to yj, okay? Then apparently there are two forces acting on this mass. The left-hand side stream force and the right-hand side stream force. And the magnitude of the force is actually T, okay? So in order to help us with solving this problem, I will define two angles, the left-hand side angle to be theta 1, and the right-hand side angle to be theta 2. Then I can now write down the equation of motion in the horizontal direction and in the vertical direction. Okay? All right. Since I have assumed that all those mass can only move up and down, that means, and also the displacement with respect to the equilibrium position, which is y equal to 0, is really small compared to, for example, the length scale A. Okay? So therefore, I can write that condition explicitly. So I have a condition. I assume that yj is actually much, much smaller than A, which is the distance between those masses. And that means theta 1 and the theta 2 are going to be much, much smaller than 1. Okay? So that actually gives us a chance to use small angle approximation. So based on this force diagram, I can now write down the two equations of motion, one in the horizontal direction, the other one in the vertical direction. So what I'm going to get in the horizontal direction is mxj double dot. This will be equal to, okay, there are two forces, right? In the horizontal direction, I would need to calculate the projection to the x direction. Therefore, the left-hand side force will give you minus t cosine theta 1. And the right-hand side of the stream force is going to give you plus t cosine theta 2. Okay? And in the vertical direction, what I'm going to get is nyj double dot. This is equal to minus t sine theta 1. Now I'm doing the projection in the y-axis in the vertical direction, and minus t sine theta 2. Okay. And since I have this condition, all the mass can only move up and down, and also the displacement is much, much smaller than A. Therefore, I have the small angle approximation. Cosine theta is roughly equal to 1, and the sine theta is roughly equal to theta. Okay? And I will call this equation number 1, and the second equation in the vertical direction to be equation number 2. Okay? So up to here, everything is actually exact. And now I would like to make a small angle approximation and see what will happen. And now equation number 1 will become nxj double dot equal to minus t plus t, and this is equal to 0. Okay, so that means we will not have horizontal direction acceleration. Therefore, in the horizontal direction, there will be no acceleration, and therefore no movement in the x direction or horizontal direction. Okay, and now I can take a look at the vertical direction. Okay, so basically what I'm going to get is nyj double dot, and this will be equal to minus t. Now sine theta 1 will be roughly equal to theta 1. So what is actually theta 1? Theta 1 is going to be, okay, so this is actually yj minus 1. Right? So that is actually the difference between the amplitude of the displacement of the mass j and the displacement of mass j minus 1, right? Divided by a, I get theta 1, right? Therefore, the first sine theta 1 will become yj minus 1 divided by a. Okay? And of course, you can do the same thing for the sine theta 2, right? Which is is actually roughly theta 2. Then basically what I'm going to get is minus t yj minus yj plus 1 divided by a. Okay? Any questions? Okay, I hope everybody is following it. Okay, so now I can actually simplify equation number 2. And basically what I'm going to get is nyj double dot will be equal to minus t over a. Basically, I take t over a out of it again. And I also collect all the terms related to yj minus 1 minus 2 yj plus yj plus 1. Okay, just actually rewrite equation number 2 in a form which we like more. Okay, so that is actually the equation of motion. So from now on, I'm going to ignore all the motion in the horizontal direction, because in this small angle approximation, we have shown you that there will be no acceleration in the x direction, right? So now it's actually getting straightforward again. Basically, we have the equation of motion, and what is actually the next step? The next step is to write down what matrix? Anybody can help me? n-1k matrix, right? So actually, as usual, we actually follow this, the procedure. Now, I would like to write down the n-1k matrix, okay? So before I do that, I will actually assume my normal mole have this functional form. Yj is equal to the real part of aj exponential I omega t plus phi. So basically, that tells you that all the components are oscillating at the same frequency, omega, at the same phase, phi. Yes? Yeah? This one? Here? Okay, maybe I made a mistake somewhere. Yeah, I think it should be plus, right? Okay. All right. Thank you very much. So now we have all the ingredients, and we assume that it has a normal mole of aj, yj in this functional form. And now I can, the next step is to get n-1k matrix, right? So what is actually the M matrix? M matrix is really straightforward. It's M, M, M in the diagonal terms, and all the rest of the terms are 0, right? And those, of course, you can also write down K matrix, right? So the K matrix will be equal to, there are many terms, and in the middle you have minus T over A, 2T over A, minus T over A, and all the rest of the terms are 0. And of course, these patterns go on and on. Minus T over A, 2T over A, minus T over A, and zeros, etc., etc. And this pattern is going to go on forever, and because this is actually an infinitely long matrix, infinite times infinite long matrix. Okay. So once we have this, we can now write down the n-1k matrix. What is actually the n-1k matrix? It has a similar structure as K matrix, right? All those are zeros. Okay, all those are other values, but it has a fixed structure, minus T over MA, 2T over MA, minus T over MA, and the zeros. And this will go on forever in the diagonal term and also the next two diagonal terms. And all the rest of the terms are 0. Okay? Any questions? All right. Okay, so that's really nice. Now we have an n-1k matrix. And the good news is that you don't have to solve n-1k matrix eigenvalue again, right? Because we have solved the eigenvalue problem of S matrix. Therefore, what is left over is to multiply n-1k by A. Right? A is actually the eigenvector, one of the eigenvector of S matrix. Okay, so I'm going to multiply that for you. And now we calculate n-1k equal to omega square A. Then I can get omega square out of this calculation. Okay? If I again focus on J's term, okay, so basically what I'm going to get is right-hand side, I have omega square AJ, okay? That is actually from the right-hand side, okay? And left-hand side, n-1k times A, what I'm going to get is T over MA minus AJ minus 1 plus 2 AJ minus AJ plus 1. Right? Because if you take this term, this term is actually in the exact diagonal, in the diagonal of this n-1k matrix. Therefore, this match with J, and this will match with J minus 1, match with J plus 1. Okay. Therefore, if you multiply n-1k and the A, you get this result. Okay. And we also know that AJ is proportional to exponential ijka, right? Therefore, I can take AJ out of this, and basically I get T over MA AJ minus exponential minus IKA plus 2, because I take AJ out of the out of this bracket, okay, and minus exponential IKA. Okay. Now I actually can cancel AJ. Basically, what I get is omega squared will be equal to T over MA 2 minus exponential IKA plus exponential minus IKA. And that will be equal to 2t over ma, okay? 1 minus, so exponential ika plus exponential minus ika, you are going to get 2 cosine ka, right? All right? Therefore, you get 1 minus cosine ka. Okay? I define omega 0 to be square root of t over ma, just to make my life easier, okay? Then what is going to happen is that I will have omega squared equal to 2 omega 0 squared 1 minus cosine ka. Any questions? Okay. Of course, if you like, you can also rewrite this as 4 omega 0 squared sine ka divided by 2, sine square ka divided by 2. Okay, so if you like. Okay, so look at what we have done. We study a highly symmetric system, which is actually shown in the slide. Okay, basically, it satisfies the space translation symmetry. Okay, then what we have been doing is to derive the equation of motion, make use of the small angle approximation. Then you will be able to find that, okay, only the y direction actually, is actually moving as a function of time. Therefore, based on this derivation of n-1k matrix, I arrive, and also based on the equation of motion, which I derived from the force diagram, I get this n-1k matrix. And since we know that n-1k matrix and the S matrix will share the same eigenvector, I can multiply n-1k matrix and the eigenvector of A. Then I will be able to solve the functional form of omega squared. And that is actually given here. Omega squared is equal to 2 omega 0 squared 1 minus cosine ka. Okay? And this is actually telling you that omega is a function of k. Okay? What is k? K is actually the wave number, and omega is actually the angular frequency of the normal modes, right? So that means what we are talking about. That means if we fix the wavelength, okay, or the wave number k, then there will be a corresponding omega. Okay, if you fix the wavelength you're talking about, then the omega is also fixed by this omega of k function. Okay, now we actually call it dispersion relation. This term may not mean much to you now, but later in the discussion, you will find out, it really makes sense, and we will talk about dispersion in the later lectures. Okay, so the conclusion from here is that basically, if I have this system satisfy this translation symmetry, then what it tells us is that the normal modes will look like some kind of sinusoidal function, right, as we discussed last time. And also, this, okay, so this is actually the amplitude, what I'm drawing here, this curve. And all those mass are only moving up and down, okay, as a function of time. And this is AJ, and the oscillation frequency, which is actually the frequency of moving up and down, this kind of motion, is actually omega. And also, we learned that omega is equal to omega of k, and that is actually decided by the length and or how distorted is this normal mole, the shape of the normal mole. And this is actually determined by the k, which is actually the wavelength, and which is actually the wave number. And of course, you can also get the wavelength from 2 pi over k. Okay? In short, if you give it a specific wave number or wavelength, then the oscillation frequency is already fixed because of the equation of motion, which we derived from the force diagram. Any questions? Okay. The last point which I would like to remind you is that at this point, since we are talking about infinite long system, therefore, all possible k are allowed, right? Because we have infinite number of coupled oscillators, and therefore you have infinite number of normal modes. So all possible k's are allowed, and that is actually because we have an infinite long system. After the break, which we will take a 5-minute break, we will discuss how to use infinitely long system to actually understand a finite system. So you will see that actually I can use now this space translation symmetry and to solve in general infinite long system, and I can actually even go back to finite system and see what we can get on there. Okay, so we will be back at 12:20. If you have any questions, I will be here. Okay, welcome back, everybody. So we will continue the discussion. So there are a few questions asked during the break. So the first question is related to how we actually arrive this equation, and that is actually because 2t over NA is actually really happening in a diagonal term. Therefore, if you multiply n-1k matrix and A matrix, which is actually shown there, then you will get this term, minus t over NA multiplied by AJ minus 1, plus 2t over NA times AJ, plus minus t over NA times AJ plus 1. And that is actually why we can actually arrive this expression. Okay? Then what happens afterward is that we found that AJ can be factorized out, and they cancel. And then now my solution is independent of the amplitude. And still, omega is actually dependent on the k value which we actually choose. Okay? The second question is, okay, why do I say k is the wave number? Okay, where is that coming from? So that is because, okay, so AJ is proportional to exponential ijka. Okay, it has a fancy name. If I take the real part, okay, as we did when we go to the description of physical system, then you get cosine jka. Okay, and j times a is actually J is actually a label, right? Labeling which mass I am talking about. A is actually the distance between all those mass. J times A will give you the x, the location of the mass. So J times A is actually the x, the x position of the mass. Okay. Therefore, if you accept that, this becomes cosine kx, and from there you will see immediately that k have a meaning, which is actually the wave number. Okay? All right? Is that okay? So that was the questions raised, which I can quickly explain. So what I'm going to do now is that, okay, we have solved, in general, an infinitely long system. What is actually the resulting normal modes of an infinite long system? It has infinite number of normal modes. And we were wondering if I can actually borrow this infinitely long system and solve finite system to see if I can arrive the solution really quickly. Okay? So the answer is actually yes. So if I consider a finite system look like this, so I have many little mass on this system, and they are connected to each other by the same strings, which I prepared before. Okay, and I call this the position in the y direction of this object y1, and the next object y2, y3, etc. And I have n objects in this system, and both ends of the string is fixed on the wall. Okay? So I can actually now argue that the infinitely long system can help us with the understanding of this finite system. Why is that? That is because now I can assume that this is actually just part of an infinitely long system, right? Okay, so I construct my infinitely long system, and now I nail the y's mass, I nail the yn plus 1 mass, and I fix that so that it cannot move, okay? So it's still an infinitely long system, but there are two interesting boundary conditions at at j equal to 0 and at j equal to n plus 1. Okay, what are the two boundary conditions? The first one is y0 equal to 0. Okay? And the second condition is yn plus 1 equal to 0. Okay? So there are two boundary conditions. So basically what I'm looking at is still an infinitely long system, but I require y0 and yn plus 1 to satisfy these two conditions. Okay? And we will find that, with this procedure, we can also solve this finite number of coupled oscillator problem. In this case, we have coupled oscillator. Okay? So the first thing which I would like to say is, based on the functional form of omega squared, that is equal to 4 omega 0 squared sine squared Ka over 2. Okay? What we actually have is that omega k is equal to omega minus k. Okay? So both of them will give you the same angular frequency. Okay? Therefore, what does that mean? This means that linear combination of exponential I j Ka and the exponential minus I j Ka, okay, linear combination of these two vectors, okay, is also an eigenvector of n-1 k matrix. Okay, so you can do a linear combination of these two vectors. Okay, so if we do that, now I can guess my solution will be like yj equal to real part of exponential I omega t plus phi. I can now have a linear combination of exponential ijk and the exponential minus ijk. Basically, I have alpha exponential ijk plus beta exponential minus ijk. Okay? And I would like to determine what is actually alpha and beta, which actually satisfy this boundary condition 1 and 2. Okay? So now I can use the first boundary condition, y0 equal to 0, right? So j equal to 0. Therefore, basically what I get is when j is equal to 0, then this is actually 1, and this is actually 1, right? So, and this actually give you y0 equal to 0. If y0 is equal to 0 at all time, no matter what t actually you give it to this system, then basically you have alpha plus beta equal to 0, right? Because j is equal to 0. So you have alpha plus beta, and that has to be equal to 0. Therefore, you can conclude that alpha is equal to minus beta. And if we use the second boundary condition, yn plus 1 equal to 0, because I nail this mass and fix that so that it cannot move, then basically what you get is yn plus 1 is equal to 0. Then basically you have alpha exponential I n plus 1 Ka plus. So beta is actually equal to minus alpha, right? So basically you can get, so basically you can get minus exponential minus I plus 1 Ka, right? Multiplied by alpha, and that is actually equal to 0. Now we have the choice. We can actually set alpha to be equal to 0, but if I set alpha to be equal to 0, then beta is also 0. Then I have 0 everywhere, right? Then there's no oscillation, and that's not fun, right? Okay? Therefore, what I'm going to set is actually the second term equal to 0. Okay? The second term, I can actually simplify that to be 2i sine plus 1 Ka. And now this is actually equal to 0. Okay? What is actually the condition of this thing equal to 0? Basically, n plus 1, n is actually a given number. A is actually the distance between those masses. Therefore, what I can actually change is the k value, right? So I can now solve this condition, and I will conclude that k will have to be equal to n times pi divided by n plus 1. I hope you can see it. Where small n is equal to 1, 2, 3, until capital N. So what does that mean? This means that, okay, originally, before I introduced the boundary condition, this system is infinitely long, okay? And it has infinite number of normal modes, right? But once I introduce these boundary conditions, which I actually require y0 equal to 0, because I fixed this point on the wall, yn plus 1 equal to 0, because I fixed also that point on the wall, something really happened. That actually gives us, first, the shape of the system when it is actually in the normal mode. Basically, the shape, what I mean here, is the amplitude as a function of j. Okay, that's actually what I mean by shape. Okay, the shape is now like a sine function. That's the first thing which we get from here. The second thing which we get here is that now the k values are not arbitrary anymore. The k values is equal to n pi over n plus 1. And the n value, the small n, is actually equal to for 1, 2, 3 until n. So now, once you actually fix this full point, you actually have only how many normal modes? N normal modes, right? So what I want to tell you is that, okay, in general, this sinusoidal shape is actually fixed already by this translation symmetry argument, okay? And once we nail both sides, actually we also restrict ourselves to the discussion of only a few k, which actually satisfy the boundary conditions. And if I plot all those normal modes as a function of I, basically what you can see from here, you can see if I have n equal to 1 and the capital N equal to 4 in this case, okay? So I have 4, basically I'm going to have 4 normal modes. The first one will be like a really long wavelength 1 when n is equal to 1. And if I increase the small n value so that the k become bigger, then you can see that there are more distortion when this system is in one of the normal mode. And this actually going to, this shape is actually going to be oscillating up and down. Instead of, okay, so all those points are only moving up and down, right? Just a reminder, okay? And why we have all those cases because of the boundary conditions. Okay, any questions? Okay, so I have several other cases, which is open end and the closed end, and also driven the coupled oscillator examples, also in the lecture notes. But unfortunately, we will not be able to go over them, but I think they are very, very detailed notes in the lecture notes. Okay, so let me, before I move on to the discussion of continuous system, okay, I would like to discuss with you what we have learned so far. So what we have learned is that if I have a symmetry, which is a translation symmetry, and plus we only limit ourselves in the discussion of oscillation, okay? In other words, we limit the amplitude so that it doesn't explode at the edge of the universe, okay? And that will give you a beta value, which is in the functional form of exponential IKA. And the equation of motion can be derived from force diagram. Once we actually derive the equation of motion, we can get n-1 k matrix. Then we can derive omega squared from this expression. And finally, we actually can simplify everything and get the dispersion relation omega equal to omega k, which is a function of k, the wave number. Before we actually introduce boundary condition to go from infinite long system to a finite system, all the k values are allowed. Once you introduce boundary condition, you'll find that you only have limited number of normal modes. Second, the k value are not continuous any value anymore. It becomes discrete, and only n values are allowed from this exercise. And finally, what is actually the most general solution is actually the linear combination of all those normal modes, which we show here, and what is actually the ratio between all those normal modes. All those free coefficients are determined by initial conditions if you are given. Okay? So that's actually what we have learned so far. And now I would like to make a leap of faith to see what happens. Okay? What we're going to do is to introduce you a continuous infinite number of coupled oscillator. Okay? So what does that mean? What I'm going to do is to go from this. So I have T and the A, T, a lot of a string and the mass system, etc., etc. I would like to go from there to just an infinitely long string, with string tension T and some kind of mass, density of mass. Okay? We'd like to make it continuous and see what will happen. Okay? So, just a reminder of the J's term of the m-1k matrix operation. Basically, we have m-1k times A. Okay, the J's term of m-1k A, that is actually given by omega square aj. This is equal to T over ma minus aj minus 1 plus 2 aj minus aj plus 1. Okay, so this is actually just a copy of that formula here. Okay, so if I make it continuous, okay, so that means what I'm going to get is omega square A, but evaluated at position x, where x is actually equal to j times A. Okay? And this will be equal to T over ma minus A evaluated at x minus A plus 2 ax minus ax plus A. Now, I'm going to make this A very, very small, right? So that when I make the A very, very small, then it becomes a very, very continuous system, okay? So what I'm going to do is I can now make A goes to 0. I can now use Taylor's series fx plus A, fx plus delta x. And just a reminder, if you do a Taylor expansion of this, you are going to get f of x plus delta x f prime x plus 1 over 2 factorial delta x squared f double prime x. Okay, so that means now I can actually do a Taylor expansion of ax minus A and ax plus A. So what I'm going to get is like this. So ax minus A will become A of x minus A prime x plus 1 over 2 A squared A double prime x. I can also do the same thing to do a Taylor expansion for ax plus A. Ax plus A will be equal to A of x plus A prime x plus 1 over 2 A squared A double prime x. Okay? Once I have done this, basically I can calculate minus A x minus A plus 2 A of x minus A x plus A. Okay, I'm just taking the middle term and copy it there. Okay, if I use now this expression, okay, then basically I will see that, okay, A of x terms actually cancel, right? Because I have 2A of x from these two terms, and they cancel with this 2ax. Okay? And also, A prime term also cancel, right? Because you have mx minus 1 and ax plus 1, ax minus a and ax plus a. Therefore, the x prime term cancel here. This is minus sign, this is plus sign. You see? So therefore, what is actually left over is all those terms. This is going to give you a double prime x a squared plus many other higher order terms, right? Because those are actually not complete. We have many, many higher order terms. Okay? In the limit of x go to 0, yes? Yeah, you're right. Thank you very much. Okay, thank you for that. So there should be a minus sign in front of it. Okay, so basically what we have is a double prime x times a squared plus some higher order term of a cube, etc., etc. Okay, since we are talking about the limit of a goes to 0, we can safely ignore all the higher order terms. Okay? So now, if we go back to this equation, omega squared a will become basically t over n minus t over n a double prime x times a squared. Okay, and the plus some higher order terms. Okay, now I can define rho L to be equal to m divided by a. Okay, and I will have to be very careful when I go to the continuous limit. Okay, I also do not want to make this system infinitely massive, right? Therefore, I would like to fix the rho L when I go to the continuous limit. So basically what I'm doing is that I cut this system in half so that a becomes smaller and the mass also becomes smaller so that rho L stay as a constant, okay, when I go to continuous limit. Okay, so what I'm going to get is omega squared a will be equal to minus t over rho L a double prime x. And to write it explicitly, this is actually equal to minus t over rho L partial square a partial x squared. Okay, because each prime is actually a differentiation with respect to x, right? Okay, don't forget what is actually this. This is actually n minus 1 k a, right, equal to omega squared a. And that is actually just partial square x, partial square a, partial t squared, right? Because this is actually n minus 1 k matrix is actually originally going back to the original equation. We are actually solving mx double dot minus equal to minus kx problem, right? So there should be a minus sign there as well, right? So nx double dot equal to minus kx. Therefore, x double dot will be equal to minus m minus 1 kx, right? So minus m minus 1 k matrix will be equal to x double dot, right? Therefore, what is actually x double dot? Is basically in the current presentation, it's actually just partial square a, partial t squared. Okay? Can everybody accept this? Okay? So now we have successfully going from a discrete system, which will have a length scale of a, to continuous system because A goes to 0. But at the same time, I fix the ratio of M and A so that the system doesn't go to infinitely massive. Okay? So if I do this, then in short, you get this equation. Partial square A, partial t squared, and that is equal to t over rho L, partial square A, partial x squared. Okay? I can now define Vp equal to square root of t over L, rho L. Okay? And this will become Vp squared, partial square A, partial x squared. What is this? This is a what equation? Wave equation. Okay, you see that now after all the hard work, okay, going from infinitely long system, discrete system, then go to a continuous limit, we discovered wave equation. This is probably the most important equation you actually learn until now. More important than F equal to NA, right? Because you cannot listen to my lecture even if this equation doesn't exist, right? Then I cannot propagate a sound wave to your ear, right? And you cannot even see the blackboard because the electromagnetic wave, which I will show it in the later lecture, also kind of satisfy the same functional form. So I think this is an achievement, a highlight of today's class. We actually realize that what we have been doing is really solving something related to wave equation. And next time, which I would like to actually discuss with you, is the solution of all these wave equations. So here I have, again, last time you have seen this. This is a coupled oscillator system. It has 72 components. As a physicist, that's actually equal to infinite number of coupled oscillator. Okay, that's good enough. And you can see that if I do this, it does something really strange, right? You see a progressing wave going back and forth, and it disappears because of friction. Okay. If I can construct something closer to a perfect coupled system without friction, what is going to happen is that this wave is going to be there bouncing back and forth forever. And that essentially can be understood by wave equation. And also, if I oscillate this system at fixed frequency, you will see that this becomes standing waves. And of course, I can do crazy things. I can oscillate and stop it, and it becomes really, really complicated motion. And of course, you are welcome to come here and pray after the class. And next time, on Thursday, we are going to talk about the solution to this equation and how to understand all kinds of fancy motion this system can do given by the nature. Thank you very much.